I'll be presenting the introductory part. Let's start with getting to know acetone. Acetone is the simplest form of ketone that could be found, and it is also known as 2-propanone. It can occur naturally in an environment, and it can also be industrial made. The chemical formula for this compound is CH3COCH3. It is an organic compound that is highly flammable, volatile, and colorless solvents. It has high miscibility in water and other solvents such as ethanol, methanol, and ether. It has a strong smell, which is commonly has the same smell as nail polish remover. On to the next part, the usage of acetone. Acetone is used to manufacture plastic, cosmetic solvent. It also can be used as domestic use, fabric cleaner, and it also used to manufacture solvents such as MMA and bisphenol A. It is one of the most heavily used solvents. It is one of the most valuable solvents. The demand stood at 7.44 million tons in the year of 2020. The largest consumptions of acetones are China, and the global market of acetone is forecasted to register a compound annual growth rate larger than 3% by the year of 2030. There are several methods that is used to produce acetone, and one of the commonly used methods is the Cumin method, where acetone is the byproduct. However, this method has shown to obtain a low purity of acetone. The other method is oxidations of propylene. In this project, we will use the method of dehydrogenations of isopropyl alcohol. Using this method, we could obtain a high purity of acetone. It is also known to have a low cost productions, and it won't yield a product that is hazardous to the health and environment.
Hello, I will present about our process flow diagram. In our process flow diagram, it consists of two feed streams, which is in stream 1, it contains isopropyl alcohol and water, while in stream 9, it contains processed distilled water. The feed from stream 1 was sent to feed vaporizer to heat, vaporize and superheated to reach 235 degree and 2.2 bar condition. Then the product was sent to reactor. In reactor, it received heat from furnace, which is from heat of combustion of molten salt. In reactor, the isopropyl alcohol reacted with the presence of zinc oxide to produce acetone and hydrogen gas. Then it was sent to cooler. In cooler, the mixture from stream 5 is partially condensed, but none of hydrogen gas is condensed. But then the product was sent to phase separator. In phase separator, the light gas such as hydrogen gas was sent to acetone scrubber to stream 7, while in bottom product, the liquid components such as water, isopropyl alcohol, acetone was sent to stream 8. In scrubber, absorption process occurred. The hydrogen gas from stream 7 was absorbed from water supplied from stream 9. Then water with absorbed hydrogen was removed from the scrubber to stream 11. Meanwhile, the other bottom product contained IPA, isopropyl alcohol, acetone and water was sent to stream 10. Next, stream 10 and stream 8 was combined and be supplied to distillation column. In distillation unit, the acetone goes to condenser, while water and isopropyl alcohol goes to reboiler. In condenser, saturated vapor of acetone was condensed to liquid. The liquid was sent to storage column, while the uncondensed part is recycled back to distillation column. In boiler, the saturated liquid is vaporized and recycled back to distillation column, while the remaining substance was removed as wastewater.
So hi, I'm Amira and I'm going to continue with the mass balance. So we choose distillation column as our non-reactive system and reactor as our reactive system. So for non-reactive system, our assumption is we take basis calculation G1 equals to 100 mole per hour. We assume the feed consists of 80% of acetone, 12% of isopropyl alcohol, and 8% of water. Given that 99.5% of the feed acetone being recovered, we assume the top stream contain acetone only and the unrecovered acetone is released to the bottom stream. So first we need to write the overall equation, and we take G3 equals to 100 minus G2 as our first equation. So at the top stream, first we can calculate the value for G2 since we know that 99.5% of acetone in feed is released at the top of the column. So since at the top of the stream is 100% acetone, we can conclude N1 equals to G2, and then we can calculate the mole fraction of acetone, which is 1.0. For the bottom stream, we can calculate the value for G3 by using the first equation, and then we calculate X2 by using acetone balance, X3 by using isopropyl alcohol balance, and X4 by subtracting 1 with X2 and X3. After we obtain all of the mole fraction of each component, we can calculate the molecular flow rate of 10 by multiplying the mole fraction with 100 mole per hour. Flowchart for non-reactive system. So next, we move to the reactive system. Our assumption is we take basis 10,000 mole per hour. The conversion of isopropyl alcohol to acetone is 90%. We assume water is 35% in the feed, and we assume the reaction is at 350 degrees Celsius and the reactor exit pressure is 1.9 bar. Our chemical reaction is isopropyl alcohol becomes acetone and hydrogen gas. From our assumption just now, we can calculate the molecular flow rate for isopropyl alcohol and also for the water. We can calculate the molecular flow rate of each component. H2 and acetone, we have the same molecular flow rate because they have the same stoichiometric coefficient. Since we not consume water in this reaction, so the molecular flow rate of water will remain the same. And finally, we can calculate the total molecular flow rate. So we need to calculate the mole fraction by dividing the molecular flow rate of each component with the total molecular flow rate. And we can tabulate our data. And this is our final flow chart for reactive system.
I will present about energy balance in non-reactive system. By doing mass balance, we can obtain the value of flow rate and component in each stream of unit. Next, by multiplying the component with flow rate of the stream, we can get the flow rate of each component. Next, we need to create inlet and outlet enthalpy table. Then, we must assume the condition of each stream and the reference states of every component. In feed stream, we assume that the condition of the stream is 45 degrees Celsius and 5 atm. In top stream, we assume that 103 degrees Celsius and 1 atm. And in bottom stream, we assume that the condition is 45 degrees Celsius and 1 atm. In determining reference state, we may put acetone, isopropyl alcohol, and water in the same reference state, which is 45 degrees Celsius and 5 atm. Next, by defining the reference state, we can obtain the H1, H2, H3 value as 0. Then we need to determine the H4, H5, H6, and H7 value. In finding H4, we need to find the summation of the heat in the change of pressure from 5 atm to 1 atm, and the heat in the change of temperature of liquid acetone from 45 degrees Celsius to 55 degrees Celsius. Then, in solving H5, we need to find the summation of heat in the change of pressure of liquid isopropyl alcohol from 5 atm to 1 atm, and the heat in the change of temperature from 45 degrees to 55 degrees Celsius. Next, in finding H6, we need to find the summation of the heat in the change of pressure of liquid water from 5 atm to 1 atm, and the heat in change of temperature from 45 degrees to 55 degrees Celsius. Lastly, in finding H7, we need to find the summation of 4 types of heat, which are the heat when liquid acetone change the pressure from 5 atm to 1 atm, the heat when liquid acetone increase in pressure from 45 degrees to 56 degrees Celsius, and the heat of formation when liquid acetone change to vapor, and the heat when vapor acetone increase in temperature from 56 degrees Celsius to 103 degrees Celsius. Next, by doing all the calculation, we could complete the inlet and outlet enthalpy table. Then, by doing assumption that the system is open system, no moving part, no significant vertical distance between inlet and outlet, we could obtain the value of heat required for the system, which is 1,308 joule per hour. Next, I will present about energy balance in reactive system. By doing mass balance, we could obtain the value of stream and component in each part. Then, we need to create an inlet and outlet table. After that, we need to assume the condition of input and output of the reactor. Also, we must determine the reference state of each component. By doing all the requirement, we could proceed in calculating the enthalpy. Next, we can calculate the enthalpy of each component. Based on reference state, we could say that the change of enthalpy is 0. However, in reactive system, we need to end up the heat of formation of each component. It is also applicable in solving H3 and H4. First, we need to find the change in enthalpy. Then, we need to end up with the heat of formation of the component. After that, by doing all the calculation, we could complete the inlet and outlet table. Finally, we could obtain the energy required by the unit by multiplying the value of component with the value of enthalpy and finding the difference of output and input. Lastly, the energy required is 71.9 joule per second.
For chapter 3, chemical engineering and fluid mechanics, there are 3 terms that we need to consider, which is the principle of conservation of mass, the second one, the first law of thermodynamics, and the third one is the product delivery strategy. Okay, the first one is the principle of conservation of mass. It stated that the matter cannot be created or destroyed. It is simply changed into a different form of matter, and it implies that only the configuration of atoms change within a reaction, and we use this to the analysis the flowing fluids. And the next one is first law of thermodynamics. It is a bit different from the previous one, which is the conservation of mass. The first law of thermodynamics states that energy cannot be created or destroyed but can be transferred from one form to another, and it implies that the energy released or absorbed in a reaction is due to the change of configuration that happen in the conservation of mass. And both of these two terms are very important in order to deliver the product, which is acetone, to the storage tank, and very important to know the strategy of the delivery. Due to the product which is the acetone is transported by using a pipeline, to the storage tank, it is very important to maximize the efficiency of the transportation process. We can calculate it, and we can know it by using the Bernoulli's equation. And some of the calculated energy that we calculate using the Bernoulli's equation might be lost due to the existence of friction force in the pipeline themselves. So first of all, the the friction pipe. The friction pipe, it depends the value of the surface roughness of the material that we use in the pipe. So the material that we use to build a pipe is stainless steel, because the stainless steel has the smallest value of the surface roughness, which is 0.002 mm. And due to that, if we calculate the friction pipe that we use stainless steel as a material, we can get a smaller number of friction pipe, and the material of pipe that we use is 0.05 meter is preferred. And for friction fitting, 45 standard elbow was chosen because the value of K of 45 standard elbow as the smallest, which is 0.3. And for the friction valve, butterfly valve was chosen, even though the butterfly valve not the smallest number of K, but they are very cheap in maintenance and very dependable. So we need, in order to build a project, we need to consider the cost that we will pay in the future, such as the maintenance. So we use the butterfly valve because of the maintenance, even though the K is 0.52. Last but not least, the friction sudden enlargement. There are a few characteristics of enlargement, but all of them does not affect the energy loss due to all have the same value of resistance coefficient, which is 1, and the sharp edges was chosen. And the last one, friction sudden contraction, and it also has a few characteristics of contraction, but we choose the well-rounded because it has the lowest value of coefficient, which is 0.04. So by using this formula, we can get the smaller value of friction loss due to friction contraction. So if we combine all the friction loss that exists in the pipeline, we can maximize the efficiency transporting acetone to the storage tank. Suggestion for storage tank: it preferred if the state of the invention is a stainless steel, because the stainless steel can avoid from rusty occur, and the size of the storage tank might be any convenient size, such as up to 40,000 meter cube, and the acetone that we fill up in the storage tank is 1,000 liter to 30,000 liter, and the rest of the volume might be used by acetone if the expansion occur. If the expansion occur at acetone, and the tank or pipe may therefore be provided with appropriate cooling mechanism, such as a cooling jacket. This is due to if the tank is in hot climates that have higher than 25 Celsius temperature, because we need to keep the temperature below from the boiling point of acetone, which is 56 Celsius, because the acetone should be in form of liquid while being stored in the tank. And the acetone spends a prolonged period in a tank or pipe, such as more than a week or even more than a month or more than 2 months.
My name is Karen. I'll be talking about conclusion. So firstly, I'll be talking about the mass balance for the non-reactive system, which is the distillation column. So the first product is actually 1 mole of acetone, and the flow rate is 79.6 moles per hour. And the second product is 0.017 mole of acetone, 0.588 mole of IPA, 0.395 mole of H2O, and the flow rate is 20.4 moles per hour. So now I'll be talking about the mass balance for the reactive system, which is the reactor. And the product from the reactor contains 5,850 moles of acetone, 5,850 moles of H2O, 3,500 moles per hour of H2O, and finally 650 moles per hour of IPA. So now I'll be moving on to energy balance for reactive system and non-reactive system. So the total energy required for a reactive system is 1.308 kilojoules per hour, but the total energy required for a reactive system is 79.13 joules per second. And finally, we'll be talking about pipe, valve, and storage unit. So the pipe that we'll be using is a stainless steel pipe, which has a diameter of 5 cm, and the roughness is 0.002 meter. Now I'll be talking about the valve that we're using. The valve that we're using is actually a butterfly valve, and the K value is 0.52. And finally, the storage tank will be made of stainless steel, so that it doesn't rust, and also it doesn't leak out the acetone outside. Thank you.